Alright, so in the last video of this deep learning with Pytorch series, I have talked about sequence-to-sequence model, and also in the end I mentioned that sequence-to-sequence model has a few of the issues which I will discuss in detail. What are those issues and how we can tackle those issues using the attention mechanism, right? So this attention mechanism is related to the bidirectional RNN. So we will use the bidirectional RNN, then we will see how the attention mechanism works, right? So let's go back to the problem which we were trying to solve in the last video, like machine translation using sequence to sequence model. So here, like, we have certain inputs, and with those inputs we kind of create at first we get the at the encoder side we get the hidden state, the h1, then using that we get h2, and then we will get the corresponding states h3, and we assume that the last state was h4. So all these intermediate states, the hidden states like h1, h2, h3, they are not being used fully. So we just hope that h4 is also kind of have the informations which are related to h1, h2 and h3, and using that h4 we kind of create our context vector. So we get the context vector here. So this is, I will mention as CV. CV is nothing but context vector. So this h4 will act as a context vector, and that context vector we pass as an input to the decoder, and decoder will start producing the output like y1, then with the help of that y2, similarly the other things in the end like yn, whatever the sequence steps we have, right? So with this we can understand that we expect a lot from this context vector, right? So we kind of expect that this context vector is kind of a representation of this full sentence, right? Which can be a problematic when we are having a very large sentence, right? So instead of focusing only the last hidden state, if we can we focus the intermediate hidden states also, right? And if we can generate the C4 or the CV, which is nothing but the context vector, with the help of all this H1, H2, H3 and H4, then we can like give lot of emphasis on the other hidden states also. And it might happen that for generating a particular step, your output vector, your output is only dependent on H2, right? So we can put more attention to this instead of uh, putting attentions or the emphasis on the other hidden vectors, right? So that is the idea when we when we will talk about attention mechanism. So here if I again take this example, like we have h1, h2, h3 and we have h4, right? Now we have a context vector, so I'm just mentioning this as C. So this context vector will not only depend on h4, so h4 it will always depend, but it will also depend on the other hidden states of my previously generated hidden state in the unroll version of RNN, right? So with that we will generate the context vector, and using this context vector we will start generating the first token and the corresponding other tokens, like this is like y1, y2 and y3 and y4. And also you need to be mindful that this context vector, for each of the output step, this context vector value will change. It's not that we have a fixed context vector. So for y1 we will have a corresponding context vector like c1, this is like c2. Similarly we will have the other context vector for other outputs, right? And this will determine that which part of the input we will kind of put more emphasis or more attention while generating the output, right? So I hope you got an overview of what is this attention mechanism, that instead of only using the last hidden state, we will also use the intermediate hidden states, and with that we will create a context vector, and that context vector will be different for each of the time steps output, right? So this is sequence to sequence with attention, right? And the other one which we discussed, which we also implemented in the last time, that was without the attention mechanism, right? Now let's go and check the detailed math of this, right? So I have this image where we have the same representation of encoder and decoder, but it's in a different manner. So if I just zoom out this, so if you see, there are few parts here. So this part which is coming up here, so that is my encoder. So I will explain each of these parts very much in detail, and this part generally represents the attention mechanism, right? And this is my decoder, right? So this is coming from the paper which was written by Bahadanu. I'm not sure like if I'm pronouncing the name correctly, but this is the one of the starting attention mechanism which came into the field, and with that, like a few later on, like few improvisation of this attention mechanism was done, and nowadays like attention is everywhere, right? So with this, let's get started. So in the encoder side, what we have is we have a bidirectional RNN, right? So this is like my forward directional RNN, and this is my backward direction RNN, right? So we have the context from both the direction, forward and backward, and each of this has a initial hidden states, which is like this one and also this one. So I will just zoom it up here. So if you just look it closely, we have two set of RNN. So these are like my forward, and this set of RNNs are going backward direction, right? And we pass our input here. So we kind of have individual words. Then we have a embedding layer. So this is nothing but embedding layer. So we pass our input tokens to the embedding layer and we get an embedding representation, and each time step we pass it through the forward directional RNN and also the backward direction RNN, and we kind of get individual RNN outputs. Like for this time step we get output like H0 forward, H0F, right? And also here we kind of get H0B, which is like a backward representation, right? So with that, what we will do next is, so for every other time steps also we will get the corresponding two outputs from forward and backward directional RNN, and once we get that, what the general tendency is to concatenate those two outputs and we get a final hidden state, right? So this H0 is nothing but a representation of H0F, which is coming from the forward direction RNN, and H0B, right, which is the representation of hidden state related to the backward direction RNN, and we kind of concatenate and we get the H0. So with that we can also get like H1, H2 and H3, right? So this is all about the encoder part. So encoder part is quite simple. Here we, instead of using the unidirectional RNN, we are using a bidirectional RNN, and we are getting the outputs from both the directions, and we are kind of concatenating and getting the each of the hidden states, right? H0, H1, H2 and H3, right? Now let's talk about the attention mechanism, how the attention is generally working. So here we have the attention layer, where we have like initially we get A0, A01, A02 and A03, right? So now let's look into this, how this A0s are calculated, and also like the individual like this E's and the capital E's, right? So we have three components which are being generated, and in the end we are getting the C1, right? We start with the H, then we get the corresponding E's, the small E's, then we get the capital E's, and in the end we get the C, right? So this is how the flow looks like, but let's look into in much more detail how the each of these mathematical steps are going on. So as I was mentioning, we have our individual H, which are like H0, H1, H2 and H3, and that we are passing to this A00, right? A00, A01, A02 and A03. So this A00 are nothing but a single layer feed forward neural network, right? So what are the inputs that are going inside this? We are having our regular H, which is coming from the encoder layer, the H0, and also we are getting the previous timestamp input for the decoder side, right? So if you see here, we have a S0, so that S0 is getting a flow here, and that is get used as a input for this A00. So with the help of previous timestamp hidden state from the decoder layer and also the encoder layer hidden state, which is 80, we get like E00, right? So this is nothing but a single layer feed forward neural network, right? So with the input of this two, we get a different representation, which is E00, right? So I hope these things are clear. Like we get E00, similarly we will get E01. While calculating the E01, we will use the H1 as the one of the input. So S0 will be as it is, right? And then we get like E02 and E03, and this all these inputs which are like E0s, we pass it through a we pass it through a softmax layer. This softmax layer will kind of normalize these values, and which would be kind of the output will be like the sum of the outputs will be 1, right? So this is how this works. So this is I am showing the calculations for E00. So we take the exponent of E00 and then we sum the exponent of each of these terms, right? And we divide this E00 exponent of E00 with the sum of this all these terms, right? So which will be like a normalized value. So all this sum would be equals to 1, right? So this one, now we kind of get the capital E's. So we started with H, then we got small e, and we get the capital E, right? So with the help of capital E's, we calculate the context vector, right? Now how this context vector is calculated, you need to look here, right? So we have our H zeros which are coming from this encoder side, and also we calculated E01, E02, E03, and um, E04, right? So with that, then we kind of multiply each of these corresponding terms, right? H0 will be multiplied by E01, E02 will be multiplied by H1. So all this will be multiplied, and we will take the sum out of this. So when we get the sum, we get the C1, right? So with the this is the context vector related to the first time step, right? So now your C1 is kind of a context vector for this decoder timestamp, right? So similarly we can generate C2, C3 and C4, right? So this C1, if I just talk about this context vector, right? C1 has access to each of these hidden states, right? H0, H01, H2 and H3, right? Now with this context vector, it can know like which part of this hidden state it should give more emphasis or more attention, right? So that is the basic concept. Like while creating this C1, C2, C3 and C4, your individual hidden states which are coming from encoder side will have a say, right? And with that it will kind of uh, understand which part of the sentence it should give more attention or emphasis, right? So I hope you got an understanding of this context vector generation, and with that context vector we will your encoder side will generate the corresponding outputs like y1, then we will generate like y2 and y3, similarly the last step output which is like yn, right? So this is how the basic math works in case of this attention for bidirectional RNN with the help of encoder and decoder architecture. So in the next video I will try to implement the same using plain Pytorch, and we will try to do the same machine translation problem with this attention mechanism, and we will see how this how the code works, right? So I hope you got an understanding of each of these components of this attention mechanism, like how the encoder works, how the attention mechanism works, and the decoder part of this sequence to sequence with attention works, right? So if you like this video, please share with your friends and colleagues, and if you haven't subscribed this channel, please subscribe. See you in the next video where we will talk about the coding implementation of this attention mechanism.